Welcome to Breadboarding. In the previous video, we managed to get an ISA bus slot configured down the bottom here and wired into the rest of our Breadboard PC bus here. And we got a VGA ISA bus video card working. There are a few issues still ongoing that I'm looking into, but it was working well enough to be able to boot into MS-DOS and to be able to do a directory listing of the disk there. So this is Breadboard PC 8088 version 2, and this is video 23, where we're going to be looking at adding an IDE Hard Disk and an IDE Controller. And in the plan that we've been working through, then in this final stage, we've just done the ISA bus socket and the VGA video card, and now we're just going to be adding the disk controller and trying to boot MS-DOS from the hard disk. There will be some links to the earlier series videos at the top right corner of the screen here, so I won't be going through some of these pages in as much detail as I did in the previous series. When I was originally looking at this, I was considering hard drives from the 1980s. Now, early PC hard drives were generally used technology called MFM RLL, were between about 10 and 110 megabytes, but they had quite complex disk controllers. Most of the electronics was on the disk controller card, and they're quite rare and unreliable. And there's actually quite a good video from Adrian's Digital Basement, which I've got here, where he was trying to get one of these 5¼ drives to be working and ended up taking it apart. And you can see here, this is the platter. So this is the recording service where the heads here record onto the disk here, and then this assembly here actually moves the drive heads across the disk, and I think this is the drive motor down here. So we're not going to be using one of these legacy hard drives there. In considering 1980s hard drives, the Compaq Despro 386, which was released around 1986, this was one of the first PCs to include the ATA or AT attachment as it's known, or later became known as Integrated Drive Electronics Drives, IDE drives. Now, original IDE drives are available on eBay for about £20 to £30 still, but again, I thought, given I already had a couple of more modern drives, I thought I'd use those. So we're not going to be using original IDE drives, but what I have got here is a relatively modern 500 gigabyte serial ATA drive. And with one of these adapters, I've got two of these adapters. One's the StarTech one, there's another no-name brand. This plugs into the serial ATA interface, and on the other side, you can just see there's the 40-pin connector there as well. So I'm going to be using one of these, and I've already used these in the Nanocomp 6809 series and in the version 1 of the Breadboard PC series, and these seem to work quite well. Now, this is the original circuit diagram from the Compaq Despro. It was actually the Despro 38625, which is one of the later ones around 1988. And the key thing here really to show is that the ATA interface to hard disk is actually quite a simple one. You can see on the right hand side here, this is the IDE connector that goes off to the drive. And if we just zoom in, you can see here we've got 16 data lines, so D0 to D15. So this originated with the PC-AT, and PC-AT had a 16-bit data bus. And there's various other control signals, things like IO read, IO write, and there's a couple of address lines as well, so A0, A1 and A2. And there's also two chip select lines. In the Compaq, these were known as CS3FX and CS1FX. And what you can see here is that the main system data bus coming in here is actually just interfaced to the ATA card using two bidirectional buffers. The 74LS245 chips that we've used quite a lot in the project already are just two bidirectional buffers with an output enable and a direction control as well. And then down the bottom here, then there is some extra buffering for some of the other signals, and there are a couple of pull-up resistors and things as well. And you can see here the CS1FX is coming in here as well. So the original IDE drives were basically just buffered onto the PC-AT 16-bit ISA bus, hence the ATA name. Now there is a project called XT-IDE, which is an open source project. The most recent version here I think is available from Glitchworks. So if you actually want to buy an IDE card, you can get the Glitchworks one here, but it is open source design. And this is a little different in that this allows an 8-bit computer such as the 8088 to talk to the 16-bit interface. And you'll see here we've got our IDE drive connector, so D0 to D15, the various other signals that we've got there. It's a little confusing, this diagram, because the bus rails are not actually really joined up, but here is the ISA data bus where we're only taking 8 bits here going into this buffer here, and then this also then connected off to the D0 to D7 over here. But then these other 2 chips are then actually used to latch the D8 to D15, so the upper byte of the interface, and this latches the outbound and inbound data. And we need to do this because we can only obviously write 8 bits at a time, and so we need to latch the upper data byte so that we can then read at a later point in time. Now, the logic down here I've already gone through in quite a bit of detail. There'll be a link in the top right hand corner here to link to the previous series video where I went through this in a bit more detail. There are 2 modes this can run in. There is the default mode, Rev 1 compatible, and there's the enhanced fast mode, and the only difference really are that the A0 and the A3 address lines are swapped around and just allows some of the writing to. And this just allows some of the reading and writing to the 16-bit data port to be a little more efficient. But we're just going to be using the default, so using the A0 and A3, not the reversed way. And when we come to look at the IDE Disk Controller Interface, the ATA interface uses 10 registers, although the address 000 here is actually the data port where we actually read and write the data to the drive. And in this particular design, then the low byte is when the A3 line is 0, and the high byte, upper byte, is when the A3 line is high, so when it's at the 8 register. If this was a 16-bit bus computer, then we wouldn't have to split the reading and writing of the ATA data into the high byte and the low byte, so it would be a bit simpler. So the terminology within the IDE specification, when Compaq originally started to use these IDE drives, they called the chip select lines CS1FX and CS3FX, and the 1FX and 3FX actually more referred to the IO address range which these were mapped to. And in fact, these then became CS0 and CS1. Now, they're a little confusing, and they're not really chip selects as such. They don't actually select between the drives. In fact, the way how you select between the primary drive and the secondary drive is actually there's a bit 4 in LBA3 register actually switches between the primary drive and the secondary drive. Now, for our design, we're only going to have one drive enabled at the moment, and the code that I'll be showing you actually uses a bit mask for 08, which is this sort of switch between this one here and this one here. And we'll see how this actually is used to toggle between the 2 bytes actually during the code. So generally the CS0 is active on writing the low byte, and then when writing the high byte, then the CS0 is actually inactive or high. So this is some of the code out of the XT-IDE BIOS. So this is the bit that actually reads and writes the data. So you can see here that it actually reads the lower byte from 300 initially, and then by XORing the IO port address, it actually switches it from 300 to 308 because BL has 08 in it, and by XORing it just toggles the bit. It then writes that byte to memory, so that's the lower byte. Then it reads the upper byte from 308 into AL. We switch the port back again for the next time round. Then we store the byte actually into memory. So what this has done is read the lower byte and the upper byte from the IDE controller and written it to memory. And then this one, which is when we're writing the data to the IDE controller, it writes the most significant byte first and then the least significant byte. So it loads the 16-bit data, so both the upper and lower bytes, into AX initially. It switches the address from 300 to 308 for the upper byte. Then actually switches the upper byte and lower byte around because we can only use AL for actually outputting data to the port. So it sends the upper byte, which is now in AL, to the upper byte port. We then toggle the port back again to 300. We switch the AL and AH around again, so now we've got the lower byte, and then we send the lower byte. Now, this code here is pretty efficient, but there is a slightly more efficient version in that if we use the fast mode, then in fact we can actually make use of in and out word. So rather than actually having to do 2 ins and 2 outs, we can actually do it as a single instruction, which is why it's a bit faster. Now, the slight change to the design, I covered this in more detail in the previous series of videos. So if you've got our IDE connector where we've got our D0 to D15 data lines, so that's the least significant byte and the most significant byte. So the least significant byte is just going to use a bidirectional buffer, just like in the original Compaq design. But what we're going to be using for the latching the data, this 74LS646 chip is quite a useful chip. It's a little difficult to get nowadays. I managed to get mine off of eBay. You can't easily get these in the DIP dual inline package form. What this actually provides is effectively a bidirectional buffer plus a latch on both sides, so a latch on both the A side and the B side. So this allows us to eliminate one of the 74LS573 latches that was on the XT-IDE design. So the upper byte, the direction A to B, when direction is high, then it goes from A to B. When direction is low, then it goes from B to A. And then we've got the lower byte down the bottom here. We can see over here we've got various control signals, so the IO read, IO write. We've got the address bus that we need here. Now the IO2 address decoder is already on the external I/O board that we've already put together with the serial port, the floppy disk controller, and the PS2 keyboard mouse controller. There is also the external I/O PLD logic, which is also providing some of the logic for things like the floppy disk controller already. And so this has all been integrated already. And what happens here is that this decoder takes our 300 range I/O enable signal with these additional address lines to produce the CS1FX and CS3FX enables, which basically enables the range of 300 and 308 to 30F. Then with the additional address lines here, when we read the data, we read the lower byte first and then the upper byte. So what we do is we read the lower byte at 300. The direction is 0. That means that the data is actually coming this way from B to A, and the lower byte has its output enable. The direction is set so the data can come out of here straight onto the data bus. But at the same time, what we also do is the clock signal and the direction here are enabled so that the data which is made available by the drive here is also then latched into the A latches on this side of the latch. However, at this point in time, this data is not available to the data bus at this point. Then when we read the upper byte, so 308, what then happens is, because the select BA is set to 1, this means that this is providing the latch data. We have the upper output enable, and then the data from the most significant byte is then available on the data bus. Then we come to write. It's a similar situation here. So the write order, we do the upper byte first and then the lower byte. So we write the upper byte to 308 first of all. So direction now is 1, so it's going from A to B. And this also clocks the data from A to B. So now the data will be on the B side of the latches of this chip. Then when we write the lower byte to 300, what we do here is the direction is going A to B. So the data will be passing straight through here to the D0 to D7. The output enable will also be enabled. And at the same time, what we also then do is do the upper output enable. And because this is selected to select AB is using the latch data, then the data that we just recorded in here is now also output here as well. So what this basically allows is the 16-bit ATA disk interface to work with an 8-bit data bus like we have in our Breadboard PC. So to summarise, it's going to be based on the XT-IDE Rev 4 board but we're going to be using one 646 chip rather than the two latches. Just minimises the bus wiring and the number of chips. We'll use the Rev 1 compatibility, so a lower speed mode for the moment. We need to configure the XT-IDE BIOS, the tiny mode, and this builds a 4K executable with Rev 1 compatibility and working with the 300 I/O port. There is a utility we need to run to configure that with the XT-IDE BIOS. We're then going to fit the XT-IDE BIOS in the first 4K of our BIOS EEPROM, and we need to then move the main BIOS to start at F9000, not F8000. Now that change has already been done because it was done in the version 1 series. We also had to modify the X-i88 BIOS when it's looking for extension ROMs to execute. We had to move the limit for the scanning from F8000 to F9000, and the start address for the X-i88 BIOS was also moved up to F9000 as well. So let's take a look at the KiCad diagram. So this is the ISA bus connector that we added for our VGA card in the previous couple of videos. Now the external I/O board has a serial port, PS2 keyboard, mouse controller, floppy disk controller, and then the IDE Hard Disk controller. We have the IDE connector here, so this is a 40-pin connector, which then has the lower byte D0 to D7, which goes through the 74LS245 bidirectional latch here, and then the upper 8 bits then go through this 74LS646 dual latch stroke buffer. And you'll see that the D0 to D7 bus is the same on both of those, then goes off to the buffers over here, which buffers onto the main data bus here. Now the I/O port decoder produces the CS1 FX, and this goes both to the IDE port and also this other external PLD up here, as does the CS3 FX, and those two signals there are then used to determine the various control signals for our latch here. So we've got the lower output enable for the buffer here, the upper output enable for our 646 dual latch here, and then the upper clock AB and the upper clock BA. So this controls the latching of the data coming from the outside to the IDE drive and from the IDE drive out to the rest of the computer. So most of the pins are already wired up for these two PLDs. We just probably need to wire in the two chip selects there and a couple of these other signals here, and then make sure that all of these data bus signals are all wired up to the port correctly. And then there's a number of pull-ups and pull-downs that we need to make sure are done properly. So we've got the grounds and various other pull-down, pull-up resistors, and there's also the LED activity here. So this tells us when the disk is actually being accessed. So if we have a look at the board, this is our IDE connector. So this is just made of some strip board, as I've done in some of the earlier videos. Just has some strip board with a hole down the middle. Then we have the I/O decoder here, the other PLD up here, and then there's the 646, takes the external data bus here, which is from here, and then this is also going to feed into this other buffer here, and then that just feeds into the lower byte there as well. So I'm just going to go off and wire that up, and when we come back we will update the BIOS with the XT-IDE BIOS and see whether or not we can start to boot up MS-DOS. Okay, so we're just going to unplug some of the existing cables around here so we can wire up the data lines between the various chips without needing to use the DuPont cables, the rainbow connectors. It just means that it's a little bit tidier. Just wiring in all of the upper data lines there, so that's D8, D15. Just tidied it up off camera there. Now just putting in all the various leads that need to be tied to ground. Then we'll just check those off. So those are all the grounds that we've wired in, the D8 to D15. Now we need to do the D0 to D7 and the other ground on the other side there. It's just wiring in the D0 to D7 data lines going to the connector there. Now we need to do, there's various pull up and pull down resistors, some going to ground, some going to 5 volts. And then we also have down the bottom here the drive activity LED that flashes when the disk's been accessed. So I think this one I put into 5 volts, it should have been down to ground when I put this in. And the activity LED. Now I'm going to tidy up the active low reset and the active high reset. So this was a circuit that I had temporarily to provide the active high reset. All I've done is taken the fly leads and just replaced these with proper cables here. And just connect it up to the serial port up there. Now we've got to do some of the control signals here. So the output enable for the lower data lines there and the data transmit receive, which tells the buffers which direction the data is going. And then that is the output enable for the lower data bus buffer there. Now we need to wire in the CS1 FX and CS3 FX, so those are some of the drive selects that control the various registers. Again, we'll just wire those in. And we also need to then put back all of the blue wires that we unplugged earlier, now that we've got all the other cables in there. Just make sure those all go back in the right place. Then make sure that the 2 interrupts there, which are for the mouse and the keyboard interrupts there. Then that's the CS1 FX and CS3 FX going up to the PLD a little bit higher up. Now we need to wire in the external address 0, 1 and 2 into the IDE connector, and also take the buffered IO read and IO write from up at the PLD up there. These are the A0, A1 and A2 lines coming in. And then that is the IO read and IO write coming from the buffer above there. Now we need to wire up the data bus connections for the buffered external IO data bus area. So this is going into the internal side of the buffer onto the main data bus there. And then there's the various control signals for the latch there. So we've got select AB, select BA and the clock AB. Now there was a mistake in the diagram here, I think, where it had been dragged. Some of the lines had got, wires had got connected incorrectly, so I was just tidying that up in KiCad. So now when we select that, it goes all the way up to the right place. And I'd also forgotten to put in the power lines for that chip as well, so just putting the power leads for that. And the select AB and the select BA being tied to 5 volts there. Now we've got the upper byte output enable to wire in there. That's been done. So pretty much everything has now been wired up. Now we'll need to build the XT-IDE BIOS and configure it. Now I have done this in detail in the earlier series, so there will be links at the top of the video here and down in the description which links to those. So first of all, we can just have a look at the XT-IDE Universal BIOS build instructions. This covers everything you need. So Tortoise SVN is needed to check out the code, which I've already got installed, and then we need to have make and NASM, and that's what we need to build the Universal BIOS. We also need to build the configuration utility as well. To start a command prompt, first of all, just make sure that we've got NASM and make installed. So you can see we've got NASM and make installed already. Then we're going to go and make the universal BIOS, and then this will produce our IDE tiny.bin. So this is a 4K executable, and then we're going to need to actually configure that. Then make all. And then we'll copy the tiny.bin over to our DOS environment. We're just going to overwrite the one that's already there. So that's copied. So now we're just going to do the configurator. Do sometimes get this error message, but it still seems to build the file okay. Again, we'll overwrite that. So now I'll just start up DOSBox and we'll have a look at the configurator. Just go full screen on DOSBox. So we've mounted our CDOS folder. That's the C drive. Go to the C drive. Go to CD XT-IDE. We can see here this is the configurator. And first of all, what we have to do is to load the BIOS from the file. So we're going to choose our tiny.bin. You'll see that that's only 3995 bytes at the moment, and the other old ones there are 4096. So you can see here that we've got the master drive. We'll just leave this as the default. Secondary drive we can disable. Now the device type, we're going to leave this as XT-IDE Rev 1. So this is the slower version of the configuration. If we use the Rev 2 version, then this actually uses a single I/O read, I/O write using the word rather than the individual byte. We'll leave this as it is for the moment. And you can see here that the I/O address is 300 and 308. Boot settings will set this to be 80 by 25 black and white. And we'll set it to one floppy disk drive. I think I remember I had some problems which seem to be resolved with that previously. And remove other hard drives. We don't want to see other hard disks which are connected for the moment. So just save that back to the original file. If we go to load the BIOS from file, you can now see that our IDE tiny.bin is now 4096. So that has been configured successfully. Okay, so we've configured that. So we just need to now burn that into the EEPROM. So XG Pro is what we use for that. So just going to read the existing EEPROM. Now what we can see here is the first 4K is currently blocked out just with the default of FF. The XT-IDE BIOS actually starts at 1000, which is 4K in. What we're going to do now is to load the XT-IDE Tiny in the first 4K and then load the rest of the BIOS above that. So this is the configured IDE tiny.bin that we just configured in DOSBox. Now we can have this start at 0 and clear the buffer as well, so that's fine for our first file here. I can see here now we've now got the XT-IDE BIOS, and when we go down to 100, you can see the rest of that is all FF. Now what we need to do is to load our main BIOS. Now what we have to do now is we want to disable the clearing the buffer, and we need to load this starting at a 4K offset. You can now see that we've got our BIOS loaded in here, so we're just going to program that. Okay, so our BIOS and the extension BIOS is all configured now, so we can put that back in the Breadboard PC. We just now need to sort out the hard disk that we're going to use to try and boot off. Okay, so as I said earlier, I'm using a 2.5-inch modern SATA drive. I think it's about 500 gigabytes in size, so we're only going to be able to use a tiny bit of the beginning of the disk. But the problem is that modern Windows, when they've been installed, install a GPT boot sector partition, and it's difficult to remove these using MS-DOS utilities. So the two ways we can do this, you can either use a wipe disk with something like DBAN, but that can take 6 or 7 hours for a disk, or we can use the Windows 11 disk part, which doesn't take very long, but we do have to be very careful not to wipe our disk 0, which is normally your main boot disk. So what I've done is I've connected this IDE drive up to a USB connector onto the laptop. And you can see here, this is the built-in disk that I've got here, and this is the second disk. So I have already wiped this, so all I did was I recreated some of the partitions here just to make it look more like a former Windows boot disk. So what we need is to look at the admin console. Then we go into the disk parts utility, list disk. We can see here that on the right hand side there's GPT, so these are both GPT. This is the most important bit. Select disk 1. Now if we do list partitions, we can now see that this is our smaller drive. So we've only got about less than 500 gigs of space here, so we're definitely on the right drive. And all we need to do to clean this is we just type clean. That's clean the data. If we go back to the disk management, you can now see that this is cleared and it's uninitialized. So as far as Windows is concerned, it doesn't know what's on this disk. So this will now mean that we can use this particular drive with older versions of operating system like MS-DOS 3.3, and we should be able to now partition that and format it from DOS 330. So once we've got DOS booting up, we should then be able to use fdisk, create a primary partition. We'll make this about 32 megabytes. We then need to set the partition to be active, reboot, and then we should be able to format it with a /s, and that should then end up with the operating system installed on the disk. Okay, so I've powered everything on, replaced the BIOS EEPROM, and we're now ready just to test things out, that things are working before we start adding anything. So just going to boot this up and check to see that we can boot up to MS-DOS. They've got the video BIOS power up, the BIOS messages, and now it's booting MS-DOS. So we've got MS-DOS 330 booting up, so that's okay. Now, one of the things we need to do is we just need to change the BIOS configuration to scan for extension ROMs in the upper area. So this is up to just below the main BIOS. So at the moment, it's not picking up the XT-IDE BIOS. So I'm just going to reboot this now. And we're going to go into the BIOS utility, just make this full screen. And what we're going to do is to enable the extension scanning. So this is going to scan in the lower area of the BIOS EEPROM, and we want this to scan. We're just going to write this and reboot. Now what you can see is the XT-IDE Universal BIOS is now looking for a hard drive at 300 hex. And if it doesn't find one, which we haven't connected it yet, so it shouldn't find it, then it should continue to boot off the A drive. So that's now still booting, so now we should now be able to add the IDE drive, and although it will find it, there won't be any operating system on it, so it should still boot off the A drive. So here we have the hard disk that I wiped the GPT partitions off here, so this is a blank disk, so now MS-DOS should be able to see this. You can see it's connected to SATA to IDE adapter, and we've got the power connectors there. I've also got the 40-way IDE cable, which I'm going to use to plug into here. So we're just going to plug this in, and then we'll see whether or not we can detect it. Okay, so I figured the cable, and I've plugged in the IDE drive and plugged it into the power. So we'll just now see whether or not we can boot this up. So it has booted up there, but it said that it hadn't found a hard disk. So I'll just need to have a look at that and see what's going on there. And when we come back, we'll see what I've needed to fix to get the hard disk being detected. So I've been looking at this for almost 2 weeks now, and I'm still not getting anywhere. So what I decided to do is plug in the Breadboard PC version 1 and to look at some of the signals on it so I can compare those with the version 2 that I'm working on. So what I've got here is the original Breadboard PC version 1, which I've got one of the hard disks installed in it. I've just got some logic analyzers set up. This one is to just check the various clock and timing signals, particularly around the bus controller. And this one is more just to record all the data bus and address bus as it actually boots up from the hard disk. I'll just switch over to the VGA capture. We'll power this on and boot it up. Tries to boot off the A drive, but there's nothing in the A drive at the moment, so then it should go boot off C. There we go. You can see here that this is booted off the hard disk here. This is one of the disks I was using previously, so this does have Windows 1, Windows 2, Windows 3 installed on here as well, and there are a few files which have been recovered from bad areas, but other than that this is working okay. Just allow me now to compare the signals against the Breadboard PC version 2 just to diagnose any issues. So after looking at the version 1 Breadboard PC and having a look at disk accesses there and analysing some of the signals, being able to capture some of the XT-IDE BIOS output messages. So this was with the Breadboard PC version 1, so you can see this is like CGA style characters here. You can see here when I tried the blank drive where I didn't have any operating system installed on it, the one that I cleaned a little bit earlier in the video, then it ends up with this no ROM basic because it can't find any operating system. And then this is the one when I actually booted it up with the hard drive I used previously, and this obviously found the ST9500 disk here and managed to boot the C drive. Now, as I was doing my investigation, I was actually able to get the new one to detect the drives under some circumstances. So in fact, I have actually got it. These are the messages. You'll see here that the version of the XT BIOS is slightly later. Here it's 2024 August and here it's 2025 September. And you can see here this is the drive ID or the blank one, and this is the drive ID for the one that I was able to get booting under the Breadboard PC version 1. So it is working to a certain extent, but it's a little bit flaky, and it can't easily get the drive identity information off of the disk so that it actually picks up the right parameters. And as I was looking into this a little bit deeper, I put the oscilloscope on the CS1 CS3 input to the IDE disk. And you can see here with the logic analyzer and the oscilloscope that there's quite a bit of interference on the active low sections of this signal. Now the signal at the top here and the logic analyzer down the bottom don't necessarily tie up to the same bit of signal, but you can sort of see that there is this sort of interference appearing on a number of the signals here and is also appearing on here. And then when we look on the CS3, then again you can see the similar sort of interference there. And I suspect that what this may be doing is interfering with the IDE drive, thinking that it's perhaps finished the current byte, and so things get out of sync and then the data doesn't quite line up when it's trying to pick up the parameters. So I'm going to go away and carry on looking at that. I'm going to finish the video here because it's been a number of weeks since I published the last video. So if you want to find out whether or not I've been able to get this drive working in another week or two's time, please hit subscribe. And if you can hit like as well, it just helps to make the videos available to more people. Thanks for watching.